When you first learn about neural networks, it's easy to assume that stacking more layers automatically makes a model more capable. You think more depth equals deeper understanding. But without one specific mathematical mechanism, an infinitely deep neural network mathematically collapses into a single flat layer. To understand why, look at how a standard node in a hidden layer processes information. It takes incoming data, multiplies it by a set of weights, adds a bias term, and passes the result forward. It is a strictly linear calculation. If you string purely linear nodes together layer after layer, the math turns against you. Because of basic algebra, nested matrix multiplications like W3 times W2 times W1x can always be simplified. They compress down to a single equivalent linear operation. This mathematical simplification means that a network with 100 purely linear layers has the exact same predictive power as a basic one-layer linear regression model. It draws a straight line. A straight line cannot model the complexities of high-dimensional data. It cannot map the intricate curves of audio waves, the spatial hierarchies of image pixels, or the contextual nuance of human language. Architectural depth provides zero benefit without a specific mathematical mechanism designed to bend the output. To learn complex patterns, the network requires nonlinearity. That mechanism is the activation function. It acts as a mathematical gate placed at the very end of each neuron's linear calculation. Instead of passing the linear result straight through, this gate transforms the output value. That transformation breaks the linear algebraic chain, allowing subsequent layers to combine those outputs and build nonlinear representations of the data. But you can't just use any function to distort the data. There is an absolute architectural constraint. The gate must be continuously differentiable. Neural networks learn backward through backpropagation. When the network makes a prediction, it measures the error and traces that error backward through the layers to update its weights. That backward tracing relies on calculating the derivatives of the activation functions. Because the derivative is used to update weights during training, the geometry of the activation function you choose will dictate whether the gradient flows smoothly or if the network fails to converge. For years, the default choice was the sigmoid function. It was popular because it takes any input and maps it into a smooth, bounded probability between 0 and 1. This chart shows the first derivatives for several activation functions. Look at the purple curve for the sigmoid function. The exact geometric shape of this derivative reveals a major flaw for deep networks. The maximum possible value of the sigmoid derivative is only 0.25, occurring exactly at the center of the curve. Everywhere else, the value drops closer to 0. Now, apply that constraint to the backpropagation chain rule. To calculate a weight update for a node early in the network, you trace an error signal backward from the output layer, multiplying the gradients from every layer that follows it. You are multiplying fractions by fractions. Multiplying 0.25 by 0.25 by 0.25 forces the gradient to shrink exponentially at every backward step. By the time the error signal travels from the output layer back to the earliest hidden layers of a deep network, the update value is so microscopic it is effectively 0. This failure state is known as the vanishing gradient problem. The network's earliest layers are frozen and cannot learn because the activation function has suppressed the update signal. To fix the vanishing gradient, the industry shifted to a more direct mathematical solution, the rectified linear unit, or ReLU. The math of ReLU is simple. Its output is the maximum of 0 and x. For any positive number, it acts as a linear pass-through. For any negative number, it outputs 0. If we examine the derivative of ReLU, the solution to the vanishing gradient is clear. For any positive input, the derivative is exactly 1.0. For any negative input, it is exactly 0. A derivative of 1.0 preserves the strength of the error signal across an infinite number of layers, preventing the exponential decay we saw with sigmoid. But that fix comes with a trade-off on the negative side of the function. If a massive weight update forces a neuron's input below 0, it instantly enters a specific catastrophic failure mode. Once that input is pushed below 0, the derivative of ReLU becomes 0. During backpropagation, any error signal multiplied by 0 is destroyed, meaning the weights for that neuron are no longer updated. This is the dying ReLU problem. Neurons pushed into the negative zone receive a zero gradient and stop participating in the learning process, which can reduce the model's total capacity. Early attempts to fix this used simple patches, like leaky ReLU, which introduced a small negative slope to keep the derivative slightly above zero and prevent permanent neuron inactivity. But modern activation functions, designed for massive, deep architectures, take a more sophisticated geometric approach, functions like swish and mish. Returning to our chart of first derivatives, look at the black line representing the swish function. It has a crucial geometric trait. Its derivative is smooth and uniquely non-monotonic. In this context, non-monotonic means the curve changes direction. Notice the specific region near the origin, where the derivative dips below zero before rising again. This geometry provides a distinct operational advantage. This smooth dip preserves small negative outputs instead of zeroing them out. It allows information to survive the negative zone, ensuring continuous gradient flow. These modern functions maintain the strong gradient flow required for positive inputs, while offering the flexibility needed to prevent permanent neuron inactivity and stabilize the training of deep networks. The activation functions we've discussed operate in the hidden layers, extracting features. But once the network completes that work, it faces a structural shift at the final output layer. The raw numbers exiting this final layer are called logits. They are unbounded geometric scores that do not yet resemble probabilities. To make sense of these scores for classification, the network requires a mathematical translator, the softmax function. Softmax applies a two-step process. It exponentiates the raw logits to force every value to be positive, and then divides each by their total sum to normalize them into a probability distribution. The softmax function serves a different purpose than hidden layer activations. It doesn't extract features, it simply translates the network's internal scores into a probability. The depth and scale of a neural network are only useful if information can flow through these nonlinear gates. In the forward pass, functions like mish or swish allow the network to break the linear chain and build representations of complex data. In the backward pass, the geometry of the chosen function ensures that the error signal isn't suppressed and that neurons remain active during training. While success depends on factors like weight initialization and learning rates, the calculus of these hidden gates remains a primary constraint. It determines whether a network successfully converges on complex patterns or fails to learn them effectively.